Let's find the Maclaurin polynomial. I'm laughing because I tried this a minute ago and I said, let's find. Let's find the Maclaurin polynomial for cosine x. And I've already started with the obvious, and I'm not going to do nearly as much on this one as I did in the last one. So let's actually jump straight into finding the values of the derivatives at 0, because it is a Maclaurin polynomial, and we'll use green. I think that's what I did on the last one. So f of 0 is 1. F prime of 0 is 0. You can see where this is going. Based on what you just saw, every other term of the cosine is also going to drop out. It's going to become a 0. F double prime of 0 is -1. F triple prime of 0, I'm amazed at that F and how it looks, but whatever. There, better. Is 0, and F to the fourth power, F fourth derivative, not the fourth power, very different, is 1. Okay, so in the process of doing this one, we will go through the same thing that we just did, but the zeros, of course, like the last one, are going to cancel out as well, and I'll probably not write all that work this time. So switch colors, and my Taylor polynomial is this. Do I need to write the general form? Never hurts. Never hurts to write it, because if you write it, then you'll remember it. So I'm going to write just about 3 terms, 4 terms, and then we'll stop there. And I'm going to go very fast. So f of 0, that's the centered, this value where it's centered, which is 0 because it's Maclaurin. X to the 0 over 0 factorial plus f prime of 0. Now, if you're strapped for time on a test, don't write this. But the more you write it in practice, the more you'll remember it. And I will go to the fourth one because I know that one actually is not going to be a 0th term or a 0 term. There we go. Okay, let's fill some stuff in. We're going to have some zeros and we'll continue this process a little faster than we did on the last one. So that is 1. 1 times 1 over 1, 1. Good to know. Okay, plus 0. Let's just not even, just don't. Let's not even, actually let's not odd. Pun intended. Ha ha ha. Let's even, let's not odd. This is an even exponent. Odd exponent. It's going to go away in this case because, I said in the last video, cosine is an even function, which has a different meaning than sine being an odd function. Sine was an odd function because if you rotate it 180 degrees around the origin, you get the same graph. Even functions have vertical rotational symmetry, meaning I can rotate around the y-axis and I get the exact same thing I had. So that one's gone, that one's gone. That one is -1. So let's not do that. Let's just go ahead and call it -1. So -1 x squared over, let's call it 2 factorial because it's good. We get to do that. And then that one's gone, and then plus 1x to the 4th over 4 factorial. We'll keep going with this process and with this pattern just so we can. And because I want to see the pattern, I like to do that, but you don't have to. So next one's going to be subtraction. It's going to be x to the 6th over 6 factorial, and then plus x to the 8 over 8 factorial. And it goes forever, and I wonder what the pattern is. Okay, we're about to find out the general term. And in doing so, we're going to, well, sniff out patterns. So this general term is a fraction with something in the denominator that's a factorial that has an exponent that's the same as your denominator without the factorial. And this, I'm screaming, I love this stuff. And this is an alternating series. So we're going to have a -1 toggle factor. There's a lot missing in that general term there at the end. Let's find it. Okay. First of all, this is not what I want to write with. This is where n equals 0. This is where n equals 1. This is where n equals 2. This is where n equals 3. This is where n equals 4. Okay? We can figure this one out pretty quickly. How do we turn a 0 into a 0? Don't do anything. How do we turn a 1 into a 2? Double it. Does that work here? Double the 0, you get 0? Yeah. How do we turn a 2 into a 4? Double it. How do we turn a 3 into a 6? Double it. So what are we doing? Doubling it. Doubling what? Doubling n to find the exponent, also to find the denominator that's going to get its factorial. So So this is 2n, this is 2n. All right, continuing this idea. I want to make sure that my exponents are going to be alternating. I'm going to make sure that my signs are alternating, and so the exponent is going to make that happen. So we are going to make sure that when I raise this to a power, I get a positive when I have an odd. And so let's do it. Here we go. If I plugged in a 0, if I plug in a 0 right there, I would get positive. That's what I want. Okay, that's good to know. If I plug in a odd, I'll get a negative, and that's also what I want. So this is going to be n right there. And that works. Works beautifully, doesn't it? I think so. So yeah, I think we've got what we need. We have the general term. It does keep going from there. So plus dot dot dot. But let's write it one more time. Final answer in purple. So that was supposed to be a cosine. Cosine of x. No. Cosine of x equals. Okay. It's the sum of an infinite number of terms. Dun, 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 dun. Starting with the 0th term, going all the way to infinity. And then, what is my general term? Well, 2n factorial, and then x to the 2n, and then negative 1 with the alternating signs. That's it. That's it. Okay. Fun time. Fun time. Let me show you what this really means. These are excellent, excellent ways to approximate functions. Now, that begs the question that has been answered before. Why would you approximate a function when we have the technology to exactly figure a function out? Because sometimes you just don't have that computational power, or you want to save your customers money by not putting some hypercomputer in whatever. Okay? So it is okay sometimes to approximate cosine, with whatever you're doing, using just a couple terms, and it is good enough, literally, for whatever you're doing, because you would be just a few decimals off, way off yonder. Okay? I want to show you what this looks like graphically, so prepare to be amazed. You're going to love this. I'll plug this up and wait for a bolt of lightning. Kaboom! There it goes. Okay, this is the graph of cosine. The red is the cosine. And that blue line is, I'm reluctant even to call it a tangent line, although technically it is a tangent line there. It is the line, you saw this with the intro to Taylor polynomials. It is the line that shows that the y value at 0 is 1. Now, if I move m forward, don't worry about what m is, but this is the, there we go. If I move that forward 1, then we have this, which is a better approximation. So here's what's happening. We're going to take that was just basically there, and it looked like a tangent line, and it was like an approximation of the slope, it looked like, but it was also an approximation of where the actual function was. Don't panic if it doesn't make sense. But the more terms I put, then the more I'll be sliding m over. That's the way this is configured. Don't worry about what the capital letter M stands for. It's just the way it was programmed. But the more I slide m over, the more terms we're going to be adding to this thing. Over here is the guts of this whole beautiful, glorious thing. See? 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 You just did this. You just did this. J equals 2, it just means that we're picking this one, okay? So that's what we're doing. J equals 2 means it's cosine. We'll finagle with another one in a minute. And the further I slide this over, the more terms I'm adding. And I hope you notice that it's becoming more and more and more accurate the further out we go. If we had an infinite number of terms, not possible, but if we had an infinite number of terms, it would exactly overlap on that line. Now, if I zoom in here, which, there we go. Can I? Yes, I can. If I zoom in here, the cosine function and the Taylor approximation are so close together, they're indistinguishable. However, the further out I go, the more I'm able to see how they depart from one another. See? Now watch this. As I continue to drag M over, they get closer and closer and closer to each other until they are basically, from what we can see from this window, the same thing. They are not the same thing, but up to a point, they're so close that you can't even tell. So, excellent approximation. This is fun. Let's keep going. Based on the way this is configured, we could change this to be, we can change that to be that. That's e to the x. Let's not do e to the x. Let's do sine x, which is j equals 3. There we go. I remember in the last video telling you that y equals x is a great approximation for sine, and it is for values very, very close to 0. See? If I was just going to hand you the line y equals x and say, what's this graph? You could say sine if you don't know any curvature to it. So it's sneaky like that. If I just graphed, nope, can't do that. If I just graphed sine and zoomed it way in, it would look like a line is what I'm trying to say. All right. The more terms I add, the better the approximation is. Man, I love this stuff. It's amazing. Or let's go back to the very first example we did in these notes, e to the x. E to the x, this is it. And this is the 0th degree Taylor polynomial, so to speak. And the 0th degree Taylor polynomial isn't even an approximation, really. It just gives me that point. That's it, just that point. And so if I get the tangent line, it's there. And then the next term up would not only give me the correct y value and give me the correct slope, it would also give me the correct second derivative. And the more I do it, the more accurate it becomes further out. Okay, so as this proceeds, as we continue with this, we will see better visualizations of this whole interval of convergence thing. Okay, so let's switch gears for just a second. And the next example we're going to do in the notes is 1 over 1 minus x, which on mine is j equals 4. Okay, the interval of convergence means no matter how far I take this out, like if I could go all the way to an infinite number of terms, there would be some point where it would fall apart. That does not happen with e to the x. If you had an infinite number of terms for e to the x, it would go all the way out. Clearly, I don't have an infinite number of terms. I've only gone up to 20, which would be 21 terms, but it only goes out so far in this. But it would eventually go out forever. Same with cosine, same with sine. However, with this one, no matter how far I go out, I will never, first of all, jump over that asymptote, and I'll never be able to get complete accuracy here. It'll never touch here. So that's the whole interval of convergence idea. So even though I've got a really good approximation around 0 and it works up to this point, it only works in this window right here from -1 to 1. So that's the beauty of Taylor series. Love it. It's good stuff. We're going to do another one in just a minute.